Welcome to Chemistry 111. Come on. There we go. Chemistry 111. We are going to try our best to finish this Lewis chapter. Now, according to my syllabus, we were supposed to finish this sometime the middle of next week, maybe the first class next week. So if we finish this today, I think it's safe to say I won't have to post a secondary lecture. It won't try to make up any classes. We'll just have, yes, last day we missed as a study day. Now, if we can't get this chapter done, we'll worry about, I'll post like maybe another video later, maybe on Saturday or something. But it should be short at worst. So let's briefly review what all we've learned. We've learned that we need to sum up all the valence electrons. We need to account for the overall charge. That step's just slightly changed. We need to select the central atom. It's usually the first atom in the elemental compound, but it's also the least electronegative atom. We can look at that chart to help that. But the trend is top right, most electronegative, bottom left, least electronegative. So left to right on the periodic table, we increase in electronegativity. 3, we connect all atoms to the central atom. 4, we distribute all the electrons to the outer atoms to give octets. If there's any electrons left, we put it on the central atom. 6, we move our lone pairs into multiple bonds to give the central atom an octet. All that's old hat. 7 is where it gets a little tricky. 1, we have to make sure that all electrons are accounted for. 2, we have to make sure that the atoms fulfill the octet and duet rule for period 2 atoms. So anything like carbon, nitrogen, oxygen, fluorine should have an octet whenever possible. Sometimes there'll be special cases with radicals or boron where we can't get an octet. And finally, we're going to minimize all formal charges to get it small and assigned to the atoms with the appropriate electronegativity. Now, there will be some times, and I'll show you in the next slide, where you have to choose between, do you want low formal charges or do you want an octet? And that when you have the expanded octet situation, you're going to be fighting those two options. And so that's what we're going to look at. So right now, we're going to actually look at some practice problems. Perchlorate, phosphorus pentachloride, and BF3. Now, perchlorate. I'm going to go into practice. Perchlorate. Starting off, chlorine should have 7. Each oxygen should have 6. 6 times 4 is 24. We add another electron for the charge. So that's 8. So we have 32 total. Let's see. Yeah, that shows up good. 32 total. Chlorine can make the most bonds. Chlorine is actually less electronegative than oxygen. And it just so happens that chlorine appears first in the chemical structure. So we're going to put chlorine in the center. We're going to put 4 oxygens around. Step 3, single bonds. That knocks out 8 of our electrons. We're down to 24. Now, this is I can only do this because of kind of like, I've seen this trend so many times. Each oxygen has 2 electrons. Each oxygen thus needs 6 more electrons to have an octet. So I'm going to put the 6 on each oxygen, and that is 24. As I said, I know those numbers because I've done this so many times. You may want to count them out each time. But as I said, this trend is something I can do bam, bam, bam because I've done this so many times. Now, there's no more electrons to place. Chlorine technically has an octet. 2, 4, 6, 8. So if I just say draw a valid Lewis structure, we're done. You might want to put this in brackets and put a negative charge, but we are done. Now, however, if we are trying to minimize formal charge, if I say draw a Lewis structure that minimizes all formal charges, let's look at the formal charge on this guy. Oxygen. Each oxygen should have 6 valence electrons around it. When we count things for the formal charge, we count half of the bonds. So 1 from this bond, 1, 2, 3, 4, 5, 6, plus that one, 7. Oxygen should have 6. Each oxygen actually has 7. So each oxygen has a formal charge of 1 in this structure. Chlorine should have 7. It has 1, 2, 3, 4. It has a formal charge of positive 3. If we add them up, 3 plus negative 4, they add up to negative 1. Still makes sense. But if I ask you to draw a structure with the least amount of formal charges, we got to do some rearranging. So what I'm going to do is I'm going to take a lone pair from one of my oxygens and bring it into a double bond. That drops the formal charge of chlorine to 2 and loses one of the formal charges of oxygen because 2, 4, 6. So I'm going to do it again. Drops the formal charge on chlorine to 1. And I can do it one more time. And now the formal charge on chlorine is 0. So an alternative structure is still the same Cl with 4 oxygens around it, but now 3 of the oxygens are double bonded, and there's only 1 single bonded oxygen. There's only a formal charge on one of the oxygens, which matches the actual charge of 1 minus. Now, chlorine actually has now 2, 4, 6, 8, 10, 12, 14 electrons around it. It has above an octet. It has an expanded octet. Is it allowed to have an expanded octet? Yes, because it is row 3. Now, if I asked you to draw a structure with the expanded octet structure or the least formal charge, you would draw this one. If I just asked you to draw a valid structure or where all atoms have an octet, you could draw the first structure. There's a lot of oxyanions that all have the same trend, where you could draw either a bunch of single bonds and give the center atom an octet, or you could add some double bonds in there to give an expanded octet. But that is the structure of perchlorate using an expanded octet. Looking at phosphorus pentachloride, you'll see here, we don't have a choice. It is actually going to be an expanded octet whether we want to or not to. Phosphorus pentachloride. Phosphorus is 5. There's 5 chlorines at 7 apiece. That's 35. We have 40 electrons. Phosphorus is the center atom. We draw 5 chlorines around it. sorry. We put a single bond to each chlorine. That knocks out 10 electrons. Each chlorine wants 6 more electrons. Since there's 5 of them, 6 times 5 is conveniently 30. That uses up all of our electrons. No more to put on phosphorus. If we look here, chlorine has 0 formal charge. 1, 2, 3, 4, 5, 6, 7. So each chlorine is formally neutral. Phosphorus, 1, 2, 3, 4, 5. Phosphorus has 0 formal charge. Phosphorus has 2, 4, 6, 8, 10 electrons around it, though. It has an expanded octet. There's nothing we can do about it. Phosphorus is allowed to have an expanded octet. And in order to make 5 bonds, it has to have an expanded octet. There's no way to avoid it. But this structure is perfectly stable. Phosphorus pentachloride has 5 chlorines around it, all single bonds, and it's happy as it can be. And let's look at BF3. BF3 is a little bit tricky. You could go with 2 different structures here. B has 3 electrons. Each fluorine has 7. So that's 21, 24 electrons. B, put the F, put the F, put the F. That takes care of 6. We're down to 18. Put the lone pairs on everything. There's all my electrons. Now, each fluorine has an octet. Boron does not have an octet. Boron actually has 6 electrons. It is not necessarily happy. We could potentially stop here because there's no formal charges. Boron is one of the exceptions. But you might want to try to draw giving boron an octet. So what would we have to do? If I did this, 2, 4, 6, 8. We could draw a double bond between the fluorine and the boron. But what would happen? Now this fluorine has a formal charge of 1, 2, 3, 4, 5, 6. So this is a positive 1, and boron would be a negative 1 on the formal charge scale. So the question is, would putting a negative formal charge on a really electropositive atom be better than just saying boron doesn't have an octet? And that is a really hard structure to say. Would it be better to put a positive on a negative atom or give an atom an octet? And that's kind of really tricky on which one would be better. And so that one, I'm not going to ask something like that on a test because that is kind of a if-then. I don't really know which one would be better. I want to show one more example, even though this isn't on the slides. But this is another oxyanion we could do. So like sulfate. It's just to show you how it compares to perchlorate. Remember, perchlorate was ClO4 1 minus, where we had Cl, double bond, double bond, double bond, single bond. Well, sulfate, this has 6. There's 4 oxygens. 4 times 6 is 24. Plus 2. puts it up to 32 again. Sulfur, single bond, single bond, single bond, single bond, knocks it down to 24 electrons. We're going to put lone pairs on all the oxygens. That uses up all of our electrons. Now, if we're comparing this guy to perchlorate, once again, each oxygen has a formal charge. Sulfur should have 6 electrons around it to have 0 formal charge. It has 1, 2, 3, 4. So it has a formal charge of 2+. So to get rid of that formal charge, we would have to make 2 double bonds. So moving one of these guys down, I'll go ahead and take that one. Move one of these guys over. Now, sulfate has 2 double bonded oxygens and 2 single bonded oxygens to give this overall charge of 2-. But so you notice, in this case, the sulfur has an expanded octet of 2, 4, 6, 8, 10, 12. Is that allowed? Yes. It is row 3. We cannot do that with oxygen. We cannot do that with fluorine or nitrogen or carbon. So the carbonates and nitrates are limited to 3 oxygens or less. So that's just an example of an oxyanion structure. Okay. One of the last major topics we will consider is electronegativity and bond polarity. We've talked about electronegativity. When we compare 2 atoms together, we can compare the electronegativity. But what we didn't talk about is what that can actually do to the bonds. When we have a difference in electronegativity, we can have what's called a polar covalent bond, or just a polar bond. When we measure this, we're often going to give a partial charge to this. The partial charge is going to be given as the Greek letter delta, the small d. It kind of looks like a note, like a musical note. It's going to be a funky looking, kind of a curvy D, and we'll either put the delta negative or delta positive. And what this means, it's saying we have a partial charge. If an ionic structure has a full-on charge, these polar bonds will only have a partial charge. But these partial charges will give it some ionic characteristic. And this, when we have these 2 opposite poles, a positive side and a negative side, we call this a dipole. And this is going to do some stuff when it comes to chemistry, especially for those of you who will eventually take organic and who need to think about how these interact. Why does water dissolve alcohol? Why does water dissolve acetone? Why does water dissolve these ionic compounds? It's because it's going to have this dipole in there. These dipoles can interact with the ions. That the larger the electronegativity difference, the greater the polarity we can see. So we could rake these guys going from purely covalent to polar covalent all the way to ionic based on how big a difference they are. And so you can see right here, this green structure is saying it's both atoms are equal, they're equally sharing. This structure where we have a polar molecule and a nonpolar molecule, we have the electrons kind of moving more so to the red side and less so to the blue side. Basically, what's happening? If I am attracting electrons away from that center, that center region, the electrons are spending more time on one side of the atom. So if probability says they're spending more time on the right and less time on the left side will see a overall lack of electrons. And so we'll see a partial positive. It's not that the electrons never go there, it's just they rarely go there. And so we see a partial positive, not a full positive. And of course, the full ionic, where the electrons have been fully removed. So now we can measure this strength as a dipole moment. We will not really bother to do this in practice, but it is possible to measure this and calculate this based on the charge and the bond distance. We're not going to really worry about this, but it basically, we can look at this as a factor of the electronegativity difference times the bond length. I'm going to skip. Okay, and the final thing we will worry about in this chapter is calculating bond enthalpy. So this is the first time we're going to touch back on the math. Technically, if you're following along in the book, they put this back in a different chapter. I'm just out of habit want to include this in this chapter because this looks at Lewis structures and it still has, I want to do this while it's fresh on Lewis structures. So one way of calculating the energy of a reaction would be to look at the strength of all the bonds. And so the bond enthalpy is the energy produced to break and make the bonds. So energy will be consumed when you break a bond. So, but on the other hand, energy will be produced when you make a bond. So when you pull two magnets apart, it will consume energy. When you put two magnets together, they will produce energy. And we can look at this to calculate how much energy will be produced. And what we're going to look at here is we're going to look at the sum of all the bonds broken minus the sum of all the bonds formed. And the net change will be the energy produced. If this number is negative, there's energy produced. If this number is positive, energy is consumed. So we can sum up all these guys. But in order to do this, we're going to have to draw out all the Lewis structures for the relevant reaction. One thing you should note as you look at this table is there's various different bond strengths. As we go into double bonds, you will get stronger and stronger and stronger. You'll have more energy that it takes to break as if we go from double to triple bonds, from single to double to triple. So there is also a correlation between bond length and bond strength. When we get to double bonds, they are shorter. Triple bonds are shorter still, so they're stronger and harder to break. But the best way to do this is to just look at this. Okay, so we want to draw out these structures and then calculate the bond enthalpy for this. So HCl, that guy's straightforward enough. HCl. This is going to come with practice, So HCl, then ClONO2. So breaking that down, how it shows, ClONO2. So let's calculate. Chlorine should have 7. Oxygen should have N. 1, 2, 1, 2, 3. sorry, this is coming from practice. This comes from practice. Nitrogen is mostly the center atom, but in this case, nitrogen has no choice but to make that has an octet, but it also has a formal charge. And we're going to go to HONO2 and Cl2. So HONO2 and Cl. One thing you should be able to note, if you are good, if you are smart, if you're savvy, you can cross out all bonds that are identical on both sides and leave only the bonds that are new. We have an NO double bond on both sides. We have two NO single bonds on both sides. So what are the two bonds that change? We have a ClO and an HCl on the left, and a ClCl and an HO on the right. So we are going to calculate the energy produced or absorbed based on those four bonds. So on the left, HCl is, got to find that, you can find that, 431, and ClO or OCl is 203. Summing those up, you get 634. And on the right side, ClCl is 242. And HO is, or OH is 63 or 83? So 463. So the sum on the right is 705. So the difference between 634 and 705 is what, like negative 71, I think. Yeah, I think negative 71. So what does this say? This reaction would produce negative 71 kilojoules. 203 was OCl. Am I reading that wrong? Okay, 203 is OCl. On a test, you would be given a chart. This chart would always be available. Let's try that again. And I will produce a couple more problems like this. Maybe ones that are even easier than this one. So negative 71 for the first guy. CH3COH. This guy is CH3COH. And HBr goes to CH3 CHBrOH. Goes to CH3 CHBrOH. Okay, so what is new and what is different? I might even have these guys drawn out for you because this is At least in this problem, it's pretty hard. Those guys are all the same. So crossing off everything that's the same. So what do we have? We have a double bond O and a single bond HBr. This time we have a single bond O, a single bond OH, and a single bond CBr. So start with a double bond O. It's on the double bond character 799. And the HBr, it's under 366. 66. Summing those up, we get 1165. And on the reactant side, CO is 358, I think. OH 463. And then CBr 276. 276. Summing these guys up. Seven. Carry that. 11, 18. Carry that. 7, 8, 9. 10. I think that's calculated right. 1097. In this particular case, you would have a positive. So positive 68 kilojoules. So it will consume energy to do this. So I'm going to quickly try to do one makeup fully on the fly, something that hopefully would be relatively easy, because these, when I attempted to do them, yeah, a little bit tricky, Let's just say let's try this. H3O plus NH3 goes to NH4 plus and H2O. This seems pretty straightforward. These are all structures we've done. H3O, well, we may not have done this guy. H3O, but O would look like this. Plus, and NH3 would look like very similar. And would be then go to NH4 plus and HLH. So what's the only real thing that's changing between the here? I can cross off 2 OH bonds. I can cross off 3 NH bonds. So what's the only thing that's changing? We are switching from an OH to an NH. An OH bond to an NH. So OH bond has 463. And an NH bond has 391. So in order to do this reaction, In order to do this reaction, we would have to absorb 72 kilojoules of energy. You could add up all the bonds on both sides. But in reality, you only need to calculate for the new bonds, because you're going to be adding 3 OHs versus 2 OHs. 3 NHs versus 4 NHs. You only need to consider what is new, what is unique when we calculate this. So I'll do one more problem along these lines, one more of relative ease with simpler compounds. Okay. Let's see. Oh, I want to do something a little trickier, but okay, let's see. Okay. We're going to do, I'm going to break this down. So we're going to have methanol plus another methanol. What is that? I'm going to combine to form a diethyl ether or dimethyl ether and water. Let's see. Actually, this, I'm not sure we can actually do this one. CO. Oh, well, no, this one's not a good one. Why? Well, because we have the same bonds on the left as we have on the right. Well, so you would have essentially a net zero, at least calculating this way, you would have a net zero change. At least it should be. It's 1, 2, 3. 1, 4, 5, 6. 1, 2, 3, 4, 5, 6. CO, 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 OH, OH. So that wouldn't actually be very useful. So let's figure out something different. So that's the problem with trying to do this on the fly. Sometimes you could have let's see. Let's do this. We'll just form what's the energy of a peptide bond forming? So OH, okay, I gotta finish drawing this. OH plus okay, we'll have a NH we're just going to a simple reaction. These two compounds are going to form water and amide. So there's a lot of bells and whistles on here, but all intents and purposes, you have N, H, and water. H, O. Once again, this is the same thing. We're losing one here. We're losing this bond there. That's only two bonds that are changing. These are only the two bonds that are changing. That structure is remaining intact as this structure here. The only difference is we are making a CN, a new CN bond, a new OH bond, and we're losing a NH and a CO. So we're only changing really two bonds in this whole structure. CO is 358. NH is 391. That's for the left side. On the right side, we're making a CN bond, which is 293. And we're making another OH, which is 463. I'm just looking them up on the table. So on the left side, adding them all up. 749. 756. The difference between these two is -7 kilojoules. So I'm just looking at simply what bonds are new between the two structures. I'm not even bothering to calculate for any of the ones that are staying the same, because they will all cancel out in the end. Now this is getting into some little trickier math, but this is where we're going to eventually go in a couple chapters. This is probably the only real math part of this chapter. And so okay, that's where we're going to end. This finishes the chapter completely. So we will not worry about making a secondary video. This is where we're going to stop. And next week, we will start chapter 7, I believe. The test is due by Sunday. Do not forget. I do not know how many people have started. So work on that.